Let us say we have a system which takes as input the signal x of t and produces an output signal y of t. This system is said to have memory if the value of the output at any particular time t naught depends on x of t1, where t1 is not equal to t naught. Okay, which means the value of the output taken at a particular time t naught depends on the values taken by the input signal at times other than t naught. If this is not the case, then we say that the system is memoryless. Okay. I'll work out a few examples, and then I will also talk a little bit about why we say that these are systems with memory and without memory. I think it's best to motivate all this by giving an example of a system that has memory. Suppose I have a system defined by y of t is equal to, say, I'll start with the easy one, x of t minus 1 plus x of t minus 2. Let's say we put a square on this, it doesn't matter. Okay, now think about, so first of all, the system has memory. Why does it have memory? Because if I wanted to compute the output y of t at any time t naught, then what I would really need to know is I would need to know the value of x of t naught minus 1, and I will also need to know the value of x of t naught minus 2. Okay, so the output at any time t naught depends on the values of the input signal at times other than t naught. Therefore, the system has memory. But I think you will get some insight into what we mean by a system that has memory if you think about how we may implement this system. So if you have to implement such a system in practice, what you need is you need some buffers, right? So what you would really need is you would have to take x of t and you have to store x of t for at least 2 seconds, such that we can produce x of t minus 2 and x of t minus 1. So in fact, if you have a buffer, or let's say if you have a 1 second delay, then we can have two 1 second delay blocks. And then this would give us the signal x of t minus 1. This would give us the signal x of t minus 2. We could take this, square it, and then we could add these two together in order to produce y of t. So the existence of these buffers or delay elements in the circuits means that the system has memory. We need to store something before we can produce y of t. Okay. Now, so that's why we say that the system has memory, or that's what it means for a system to have memory. It may be a bit confusing that sometimes y of t may depend on x of t plus 1, for example. Okay. Now I would strongly urge you to watch the video corresponding to causality. I made another video where I talk about when a system is causal and when it is not causal. Okay, I think it would be a good idea to watch that video to understand how we can implement systems for which y of t depends on x of t plus 1 or t plus something in general. So another example of a system that has memory according to our definition. So here is a system that has memory, say 2 times x of t plus 1 minus 3 times x of t. So again, the system has memory because y of t depends on some value of x of t at a time other than t. Okay, in this case, we really have to look ahead in the signal. We have to look at the value taken by x at a time that's 1 second more than the current time in order to be able to produce the output y of t. So these two are systems that have memory. So here are some examples of systems that do not have memory or memoryless systems. Of course, the easy one is this. Say if I had a system which was just outputting the cube, or it takes x of t, raises it to power 3, and that's the output. So clearly this system is memoryless because y of t depends only on x of t. Okay. But often students get confused by the statement that I just made when I say y of t depends only on x of t. So I want to clear this confusion, and let's look at another system of the following form. Suppose I have this system, y of t is cosine of t plus 1 times x of t. Does this system have memory or not? The answer is this system does not have memory. It's a memoryless system. Now what is confusing to students is, sometimes students have asked me, oh, you told me that a system is memoryless only if y of t depends on x of t. Well, that's really not what I said. It does not. If a system is memoryless, the output y of t does not depend on x of t for some other value of t. That's all it means. So they get confused by the fact that here is a term cosine of t plus 1, and y of t depends on something other than x of t as well. Well, sure, it depends on something other than x of t, but it does not depend on the value of the input signal at any other time than t. Okay. They also get confused sometimes by the fact that they see t plus 1 here, or and think that the output at time t depends on something at another time. Okay. This is also wrong. The t plus 1 here is not something that requires memory to have to implement, because I can always think of this as some function of t times x of t. Okay, in other words, I can compute the value of cosine t plus 1 at time t. I don't have to wait for 1 second in order to be able to compute cosine t plus 1. However, if I had x of t plus 1 or t minus 1, then that is a system that has memory. Okay. Similarly, if I had sine t minus 2 times x of t. Now clearly this is memoryless also. Do not get confused by the fact that you see a t minus 2 here. What we should not have is x of t minus something. Okay. I mean, the same thing applies to discrete time systems as well, and so I'm not going to specifically talk about discrete time systems. Now sometimes the only thing that you may have to be a little bit careful about here is sometimes this relationship between the x of t and y of t may be a little bit tricky. So I will try to give you another example here. Suppose I had the system y of n is equal to y of n minus 1 plus x of n. Okay. Now if you look at the system just as it is, you may think that, well, y of n depends only on x of n. But this is actually a little bit tricky, because if you start to write, let us say we have some initial conditions. Suppose we know that, say, y of 0 is 0 and x of 0 is 0 as well. So we get that y of 1 is equal to x of 1, but y of 2 is equal to y of 1 plus x of 1. If you just look at this here, it appears as though y of 2 depends only on x of 1. But the problem is y of 2 depends on y of 1 also, which in turn I'm sorry, this must be x of 2. Y of 2 depends on y of 1, which in turn depends on x of 1. So actually y of 2 is x of 1 plus x of 2. Okay, so the system does have memory. Okay, you could argue with me saying, look, I mean, I don't really have to explicitly store the past values of y. That is true, that you do not have to explicitly store the past values of y. I'm sorry, past values of x. So let me just repeat it for the sake of clarity. You may argue with me that I don't need to store all the past values of x in order to be able to implement this system. That is true. However, you will need to store the past value of y in order to be able to implement this system. Okay, so the best thing to do is to get an explicit relationship between y and x, where you have a relationship where the dependence between y and x is very clear. In other words, you do not have any terms that depend on x other than like of this form. And then you see whether y of n depends only on x of n, or if it depends on other values of x as well. I think that's pretty much what I have to say about systems that have memory and don't have memory.